So we're starting chapter 18 now. Chapter 18 is reactions at the alpha carbon of carbonyl compounds. So we're familiar with carbonyl compounds. We've looked at the reactivity of the carbonyl carbon and then what happens to those things that add to the carbonyl carbon. What we're going to see in this chapter and the next chapter is that carbonyl containing compounds have another type of reactivity. The picture here, just so you know, some of the reactivity is reluctant reactivity, and we have to use fairly harsh reagents at times. Sometimes we have to use this reagent, which is actually T-butyllithium. You don't normally use it in this fashion. It's very reactive. This is just showing you how reactive it is. It just, when you squirt it out of the syringe, it starts reacting with water in the air, and then just, it's so exothermic, it just takes off and it just burns spontaneously as you squirt it out in the air. And that's unfortunate that we have to work with such dangerous reagents sometimes. You will never work with this in an undergraduate lab. There was an accident in California a few years ago where a postdoctoral researcher died as a result of improper use of reagents, and the professor is actually being taken through the courts. There's some arguments about that. I actually think that the professor, he let an untrained graduate student work in an unsupervised lab. That shouldn't happen, okay? So you guys should not be asked to do things in an unsupervised lab, particularly if you're unfamiliar with things. Now, again, you will never have to use this reagent in an undergraduate setting, I think anywhere. So let's take a look at, oops. Let's take a look at the reactions at the alpha carbon. So the alpha carbon, when we have a ketone, we can, instead of numbering those carbon atoms, we give them Greek letters, and we just go alpha, beta, gamma, delta through the Greek alphabet. And if we're talking about carbonyl chemistry, that will be our starting point. We may be talking about an alkyl bromide. It's whatever functional group we're interested in. So in this case, we have to go both ways. There's two alpha carbons then in a ketone. In an aldehyde, there would only be one alpha carbon because the aldehyde, do we have one up here? Well, we don't, but we have this. Here there's only one alpha carbon because on the other side it's interrupted by an oxygen, and that's a different functionality. So the alpha carbon is bonded directly to the carbonyl carbon. Because of the electron withdrawing nature of carbon, that actually affects the acidity of the protons that are on that carbon. So we're used to seeing a nucleophile attack the electrophilic carbon, but what we're going to find out today is that the carbonyl group can impart a different reactivity on other portions of the molecule. And here's a number of different groups, and all of these things, all of these carbons are to more or less degrees electrophilic, all of these carbonyl carbons. But what we're going to find is that there's other points of reactivity. For instance, in this one, not only is that an electrophilic carbon, but this beta carbon is also electrophilic. Now, the alpha hydrogens are weakly acidic because of the electron withdrawing nature of the carbonyl group. And by weakly acidic, they have pKa's between 18 and 21. That's not really very acidic, but relative to, if we have a strong enough base, we can remove that proton to form this anion. Now, hopefully we recognize right away that that anion can actually has a resonance structure where we put the negative charge on the oxygen. So we do this just by moving the electrons to form a carbon-carbon double bond. When we do that, we have to push these electrons up onto the oxygen. So the real structure of this compound is not represented well by either of these, but it's represented by the hybrid. So there's a lot of charge density on this oxygen, and there's a lot of charge density on that carbon. Hopefully, and that thing is what we call the enolate anion. When we remove the proton from a carbon alpha to a carbonyl group, we get an enolate anion. Okay, so to be sure, the protons on the alpha carbon are only weakly acidic, but let's compare it to other hydrocarbons. A simple hydrocarbon, something like ethane, all these protons are equivalent. They're not very acidic at all. The pKa of that is 50. We need really, really harsh conditions to remove one of those protons and be left with that anion. As soon as we make an sp2 hybridized, they become slightly more acidic, and that's because now this is sp2 hybridized. We talk about that carbon having a lot of S character. The electrons are pulled tighter to the nucleus. The nucleus is positively charged, so it's better able to support a negative charge. When we hybridize even further and we get to sp hybridized carbon, these things actually become acidic enough that we can work with them. We don't even need to use extremely harsh bases. We can use bases like amides to pull that proton off. And then when we put a carbonyl group over here, they become more acidic. So 18 to 21, I said some books will tell you 19 to 20. It depends a lot on what's over here and what's over here. So they are considerably more acidic than the protons on simple hydrocarbons. To be useful, they need to be the most acidic protons on the molecule. So we need to be able to start taking a look. We're starting to get a lot of chemistry with different functional groups. We need to now be able to look at molecules and start assessing where they would be reactive. So here we've drawn a ketone, and I've just made the acidic protons blue, and they're the ones that are closest to the carbonyl group. These would all be relatively acidic, at least relative to the rest of these. They would be the most acidic protons on that molecule. Now, what other kind of reactivity does that molecule have? Well, we can't forget that that carbonyl carbon is electrophilic, and things that are bases often can act as nucleophiles too. So we're going to have these competing pathways. Now, one of the things that is helpful for the removal of these protons is oftentimes a base, even a base like an alkoxide, is going to add to that carbonyl carbon. But it's going to add, and then there's nothing else for that intermediate to do, and it comes off. It's an equilibrium. It jumps on. It exists for a while as the alkoxide from the addition, and then it leaves. There's an elimination. It has nothing to do once it's at the alkoxide, and what happens is it comes off, and every once in a while, instead of adding there, it abstracts a proton. And when it abstracts a proton, it forms that enolate, and that enolate probably has something to do. At least if we're the chemist, we're going to arrange for it to have something to do. So we want to set the conditions up so that if we get an electrophilic attack on the electrophile from our base instead of abstracting the proton, we want to make sure that that tetrahedral-intermediate has nothing to do, so that it just goes back. And then when it forms the enolate, we want chemistry from it. We try to arrange the conditions. But obviously, if we take a look here, this is the most acidic proton on this molecule. So even though these are more acidic than this, if we react this with any kind of base, this is so much more acidic that it's going to, the proton's going to be removed, and the equilibrium is going to lie very much to the carboxylate. So it would be hard to get any chemistry from these. We need to be able to assess these things. Over here, what about this? This actually is not a particularly strong acid, so these protons remain more acidic. This one doesn't. This is a base in functionality, and this base is not a real strong base, but a pretty good base. It wouldn't pull these protons off to any significant extent. So we do have the possibility to do some chemistry by pulling off those protons. What if we, instead of a amino group, we have a hydroxyl group? The pKa's for these alcohols is around 16. So they're better acids. Remember, the lower the pKa number, the better the acid. The pKa for this, 4.5, 5. pKa for this, 15, 16. pKa for these, 19 and 20. So this is a stronger acid, and it's going to compete with these very well, actually. In fact, it's difficult to do any kind of enolate chemistry with these things because that is too much more acidic. And we get down to here again. We talked about this being acidic. The pKa was 25. It's considerably less acidic than these protons, so this shouldn't interfere if we're trying to do acid-base chemistry with these protons. You need to be able to make those assessments. They can be helped. So these are the more acidic. These are more acidic than the alpha hydrogens just on those two functionalities. So in terms of enolate chemistry, we wouldn't be able to use substrates like these. Okay? I've uploaded to Acorn a chart, a pKa chart that tells you the pKa for these different acid-base reactions. So for instance, 1,3-diketones, look at that, pKa is 9. That means it's relatively acidic. It's much more acidic than just a regular ketone. Regular ketones, do we have them on here somewhere? There we are. So to pull off one of these protons, the range is 18 to 21. So there's a table and there's 2 pages. It has strong acids on there as well. And these are kind of, you should be able to assess most of these. You should be able to look through these and say, yeah, that makes sense to me. And I suggest that you do that because you're getting to the point where we're having so many reactions that we have to be able to make some assessments of which reaction pathway is going to go. So ketones can undergo this. It's called a tautomerization. The tautomer is simply an isomer. So a proton moves from this carbon to this oxygen, and the double bond moves from here to form this thing. These are in equilibrium. That equilibrium, we're going to find out, it's a slowly established equilibrium, but it's not very significant either. We'll find out that most of the time, this is the favored by quite a lot. So 6,000-7,000 times more in this form than in this. These things we're used to seeing. They're electrophiles. Quite often, if you see colors, blue is for electrophiles, red is for nucleophiles. I'll sometimes make particular parts of a molecule blue or red. That's indicating its nucleophilicity or its electrophilicity. So ketones, we have been used to seeing them as electrophilic. We know that oxygen is basic, but most of the reactions we've seen with ketones so far is as electrophiles. Nucleophiles attack the carbonyl carbon. We've talked about the alpha CH protons are acidic. We've talked about that. Another thing that's interesting about ketones, they're hydrogen bond acceptors. Hydrogen bond acceptors only, really. Enols, on the other hand, their reactivity is typically as nucleophiles. They're nucleophile. The alpha carbon attacks electrophiles. So in fact, we could imagine that this nucleophilic carbon could attack this electrophilic carbon on another molecule in the system. And we'll see in the next chapter that happens. The OH bond, the OH proton is acidic. And in fact, because if we remove this proton or this proton, we get the same species, right? We get that enolate. Doesn't matter if we remove it from here, we get an enolate. Then if we remove it from here, we actually get the same enolate. They're just resonance structures of each other. So the pKa we would expect to be the same. These are both hydrogen bond donors and hydrogen bond acceptors. There's the OH that can be the hydrogen bond donor. So a couple of things. It's just an equilibrium between isomers. We have to actually move an atom from there to get from one to the other. So don't confuse these with resonance structures. Under most conditions, the keto form is favored. Under most conditions, not always. So this is just showing for acetone itself, for acetaldehyde, it's almost predominantly in the keto form. Now, that's presuming there's no water around. If there's water around, this is mostly in the hydrate form, right? So we can't forget about that. Acetone, mostly in the ketone form, but significantly more of the enol around, at least than here. As soon as we get to cyclohexane, now we're getting a significant amount of the enol, and we can expect to start getting some chemistry from that enol. When we get these beta keto compounds or beta, what do we call this? We'll see it in a second. It's a diketone, a 1,3-diketone. These actually are quite acidic, and also the enol form is fairly prevalent. Now these proportions are very solvent dependent as well. If we have hydrogen bond accepting solvents, it tends to favor these types of compounds. Hydrogen bond donors tend to favor the keto forms. But we have a significant amount in the enol form. We'll see why. We'll see more of these species today as well. So the reactions of enols and enolates. The first reaction we want to look at, if we have this compound, notice there's a stereocenter here. We can synthesize this, and what we will find is if we dissolve this in a very nice dry organic solvent that has no available protons, no significant basicity, it lasts for quite a long time. If we put it in something like ethanol, it doesn't last nearly as long, but it still lasts for quite a long time. If we drop a little bit of acid in or a little base, we can very rapidly see it just racemizes, okay? And what's happening? Why is that racemization so facile under conditions of acid or base? What happens is we form the enol, and this is in equilibrium with the ketone form, but when it gets to this enol, we no longer have a chiral center, and it can't decide. It has an equal likelihood of going back to the same enantiomer or forming the other enantiomer. So that proton, when it comes back, it can come back and land on top, or it can come back and land on the bottom, and we get a racemization. So we talk about what does the acid to do. In aqueous ethanol treated with a small amount of either acid or base, the solution loses its optical activity, and this is due to racemization via its enol. Let's take a look at the enolization, and it can be catalyzed by acid or base. If we have a base will come along and remove that proton to form the enolate. The enolate, that's in equilibrium. The enolate can just pull the proton back off of that base, and we get this equilibrium established. And when it pulls that proton off, if it pulls it off with the oxygen, we get the enol. If it pulls it off with the carbon, we get the ketone. Okay? Now, what we want to realize is this equilibrium will be there no matter what. But if we're trying to do reactions with this, as we strip it out, it's going to take time for the equilibrium to be reestablished. If we have a little bit of acid there, it just makes this equilibrium very fast. It can also be acid promoted. We know that ketones can act as bases and pull off a proton from an acid to give us our protonated compound. And then we can remove this proton and give us the enol. If the base comes along and removes this proton, we get back the ketone. So I don't want you to confuse this fact that we talk about the acid-catalyzed enolization, forming of the enol. That happens anyway. It just happens really, really slowly unless we have an acid or base around. If we have an acid or base around, that equilibrium is really, really rapid. And so if we get any chemistry on the right-hand side, it gets reestablished, and we can get a lot of chemistry from the right-hand side. If we don't have acid around, that becomes very slow because the establishment of the equilibrium is very slow. So let's take a look at some chemistry that we can do things. One of the things we can do is we can take a ketone, and it has an alpha carbon that has a proton on it. You must have an alpha carbon with a proton on it to form the enolate or the enol. If we react this thing with a halogen, we actually get a substitution reaction where we substitute that hydrogen for the halogen. The other part of the reaction just gives us our halic acid. So the first step is slow. It can be catalyzed by, it can be base promoted or acid catalyzed. If we have base, this is the slow step in the reaction. It's formation of the enolate. The enolate is a very good nucleophile, and it will quickly react with our halogen, where the electrons on the carbon will reorganize, abstract one of the halogens, and break this bond. So it abstracts kind of the positive halogen, and we knock off a negative halogen over here. So this is our product, and this will just combine with the proton that was pulled off by the initial base. That's our halic acid. So this part of the reaction is fast, and it is this equilibrium that is slow. The formation of the enolate is the slow part. Enolates are very good nucleophiles, and they'll quickly react to form our substituted ketone in this case. So evidence that this mechanism occurs comes from the fact the initial rates are independent of the halogen. That's because this is fast. This is slow, this is fast. Remember back from first year, so we talk about this as being the rate determining step. They're dependent on the concentration of bases. If we add more base, this reaction goes much faster. It's difficult to stop at just one substitution because the product has a lower pKa. This, if there are more protons here, they become more acidic than that proton was because of the electron withdrawing nature of the halogen. So it's difficult to stop at just one. If there are multiple protons on our alpha carbon, we will get multiple substitutions of those protons. This can also be done under acidic conditions. In this case, the slow part of the reaction is the formation of this enol. Then that enol is a pretty good nucleophile, and it just abstracts the bromonium from the bromine and kicks off bromide, or halide, I should say. And this thing is just our protonated ketone. The base will come along, remove that proton, and we get our substituted compound. Okay? And again, the rate is also independent of the halogen. This one is a little easier to stop at monohalogenation, but we can still push it and get multiple halogenations. A special case when we have methyl ketones, we do this with our halogen in excess and some base, and we end up getting the carboxylate and iodoform that comes out as a precipitate. So what's going on here? The initial halogenation is the same. It's the same thing, but what ends up happening when we get to here, we've put so many electron withdrawing groups onto that carbon that this now becomes a good leaving group. So we'll take a closer look at the mechanism, what happens. And I want you to think, this is the same as we've already seen, and then this reacts a lot like the hydrolysis of an ester that we did last in chapter 17. So the initial mechanism is just the same, where we put our halogen on the alpha carbon, and this just happens 3 times till we get to there. So once we get to there, as we put more and more electron withdrawing groups in this carbon, we're making it a better leaving group. We're also making this more and more electrophilic. So remember I talked about how our base can add to the carbonyl carbon and form this tetrahedral intermediate, and it just can't do anything. It just goes back, okay? Once we put 3 of those halogens on here, now all of a sudden this tetrahedral intermediate can do something, okay? It can go forward. Up until that, when we have less than 3 halogens on there, the only thing it can really do is go back. Now, it can reorganize to reform a carbon-oxygen double bond, but instead of kicking the hydroxide out, it can kick out this CX3 minus. That's fairly stable. It's not real stable, but when it's born, the very, very instant that it's born, that it comes into existence, this negatively charged thing, look what's next to it, a carboxylic acid, okay? And so instead of this attacking, when these things bump into each other again, it just pulls that proton off because it's so much more acidic, and we end up getting this. It is this last reaction that drives us. Just like in the base-promoted hydrolysis of an ester, this last step drives the reaction. It's the reaction it's a weak base, but it's a good weak base, pKa around 4.55. And this is a strong enough base that the only thing it's going to want to do is pull off that proton. It's not going to attack the carbonyl carbon. It's just going to pull off that proton, and this drives the reaction. If we want the carboxylic acid, we would now do what we call quench the reaction by adding something like HCl or some other strong acid so that we could protonate this and separate it. As it turns out, if we're using iodine, if we're using iodine, this comes out as a yellow precipitate. This used to be used diagnostically for structure determination before the advancements of the modern spectroscopic instruments that we have now. Structure determination was often done chemically, and we would look to see if we had a methyl ketone by doing this reaction and looking for a yellow precipitate. That was indicative that we had a methyl ketone. It's called the iodoform reaction. Oh, the next reaction we want to look at is the halogenation of the alpha carbon of carboxylic acids. It's called the Helmholtz-Zielinski reaction after its founders. We can take a carboxylic acid that has protons on the alpha carbon, and we can react it with a halogen in the presence of phosphorus. We often add other things like if we're using bromine, we would add PBr3, and we end up getting the halogen on that alpha carbon. So it's kind of an interesting reaction because I told you a while ago that even though these are acidic, this is much more acidic. So what's going on in this reaction? Well, the actual reaction makes this thing first. It makes a acyl halide, and it's that acyl halide that then undergoes substitution. So our initial product is actually this. This is the first step, and this is the product. This product is very reactive, reacts readily with water to give us the substituted carboxylic acid, because this acyl bromide is very easily quenched with water to form the acid. So even though this is our initial product, it's never isolated. We isolate the alpha bromo carboxylic acid. And the yields are pretty decent, 77% in this case. So what's going on? The first step in the reaction, the phosphorus reacts with bromine. We form in situ this PBr3, and that acts as our acylating agent. And then that thing can enolize to form the enol, especially under these highly acidic conditions. Even though this is not very favorable, the equilibrium is very rapid because of the acidic conditions. And this thing is nucleophilic and ends up forming our initial alpha bromo acyl bromide. This thing then reacts rapidly when we work it up with water. We let this reaction go to completion, then we quench it with water to get the carboxylic acid with the halogen in that position. So the first step of the reaction is formation of the acyl bromide, and that can be in equilibrium with the enol of itself, and that is the reactive nucleophile that gets brominated and ends up giving us our final, our intermediate product, which is quenched to give us our final product. These things are useful because we can use them to make alpha hydroxy acids, which the cosmetic industry makes a lot of these. They use them for chemical peels and stuff. And also we can use it to make amino acids. And we can make different amino acids through this. We probably would never use this reaction to make glycine. Glycine is cheap. You can get it from biosources. But you can do that reaction. Okay, the next one we're going to talk about, this is a little bit different now. This is actually where I started started to understand chemistry when I was a student, was when we started talking about these things. So we know that these are fairly acidic, but if we use a base, even a base like ethanol, the conjugate acid of that base is a stronger acid than our ketone. So even though we have this in equilibrium, it's going to lie very much on this side because this is not a strong enough base to significantly pull off a lot of protons and make mostly the enolate anion. But we could use stronger bases. If we use a very strong base, we can push the reaction to favor the formation of the enolate. So one strong base that we use a lot is this thing called lithium diisopropyl amide. It's just two isopropyl groups and a nitrogen with no proton on there. It's been removed. It's negatively charged. It's a very strong base. The pKa for this conjugate acid, 38. That's a terrible acid. And remember, the weaker the acid, the stronger is its conjugate base. And organic chemists often talk about a base strength by speaking of the pKa of its conjugate acid. So you'll hear sometimes an organic chemist will talk about, oh, lithium diisopropyl amide is a very strong base. It has a pKa of 38. They're not really being correct. They're saying the pKa of this is 38. But that tells us that this is a very strong base because its conjugate acid is a very weak acid. The weaker the conjugate acid, the stronger is its base, okay? So this is a very strong base. This reaction pretty well goes to completion. Notice we don't have the equilibrium arrows anymore. The pKa of this acid, 38, of this acid is 19, so this base is going to rip it off and it's going to lie over here. It's just going to sit as the, that should be a lithium, by the way. I got this from the publisher because we use lithium diisopropyl amide. This should be a lithium enolate. I'll try and fix that. So why is that useful? This actually enables us to prepare the reactive enolate and then add a reagent to it to react with it. And that can be advantageous. So we talk about these things as being lithium enolates. Lithium diisopropyl amide, it's typically made from butyllithium and diisopropyl amine, and that gives us this. The conjugate acid of this, which is just butane, has a pKa of 50, so this reaction also lies very far to the right. So now you might ask yourself, why not use the butyllithium as the base? Why not use the butyllithium as the base? Well, if we take a look at this, we have two big isopropyl groups bonded to the nitrogen. We're kind of making the basic site a little bit inaccessible, so a tiny little proton can get in there, but this thing is not a good nucleophile. Because of that, we've bulked it up sterically. We talk about it being a non-nucleophilic base. It's not a good nucleophile, which is important because we have those electrophilic carbonyl compounds, and if it did attack the electrophilic carbon, that intermediate would be much more stable than this anion, and it wouldn't be a reversible addition to the carbonyl carbon. So we have to use a non-nucleophilic base. Now the fact that we bulk it up has another advantage too. It actually prefers to pull the most sterically accessible hydrogens off of a compound. So if we have ketones such as this, we have 3 protons on this carbon, 1 proton on this carbon. We all have tiny little, those protons are very easily attacked by the base. This proton is somewhat protected because of the steric bulk around it. We actually favor, more often we're going to pull this proton off than pull this proton off. In fact, we can almost exclusively make this enolate that comes from pulling this proton off. So we only get this enolate and we don't get the enolate which would result from pulling that proton off. So that's another advantage. That gives us the opportunity to do some regio-specific reactions. We don't have to worry so much with this very strong base of pulling off this proton, and we can react at the less steric site. If we used a weaker base, we actually we'll see in a minute that we would favor the pulling off of the other proton. So if we had this ketone, notice that we have a methyl group there, and we don't on this side. So we talk about if we use weak bases, notice that this enolate is a more substituted enolate. We have 1, 2, 3, 4 substituents. There's no hydrogens bonded to that. So that is thermodynamically more stable than this enolate, which has 1 proton still on it. Remember when we talked about alkenes, the more substituted alkenes are more stable. So this enolate is thermodynamically more stable than this enolate. And if we do the reaction with a weak base, everything is in equilibrium conditions, we're going to have more of this in solution than we would have of this. If we were using a weak base, this would be the dominant species, but we would have more of this than this. We wouldn't expect their reactivity as nucleophiles to be much different. We're going to end up getting more product from this than from this. If we use a very strong, non-nucleophilic, sterically bulky base, we will form this almost exclusively, and we can get all of our chemistry to occur from this. We call this the kinetic enolate. It's thermodynamically less stable, but it forms much faster when we use a big bulky base that's a strong base and doesn't have the opportunity to pull off that proton from this sterically hindered position. So we can get kinetic control, and if we use weak bases, we will get thermodynamic control. We talked about thermodynamic versus kinetic control before. You have to have special circumstances. You have to have a case where this is thermodynamically less favorable, so then we can then switch the reactions. Weak base, most of our reactivity will come from the thermodynamically more stable base. Strong, bulky base, and our chemistry all comes from what we call the kinetic enolate. So if we were to take this, treat it with some LDA, we would make this base. Here is our nucleophilic carbon, and it will undergo SN2 reactions with primary alkyl halides to form our substituted compounds. Yields aren't great, but we do get most of our chemistry coming from here. It's interrupted a little bit by some other side product, but we can easily purify these, and we get predominantly the one product. So the mechanism of this alkylation is SN2. This plus this is an SN2 reaction. This plus this is an SN2 reaction. That means we cannot use as our alkylating reagent, our alkylating agent, we can't use tertiary alkyl bromides. What happens with tertiary alkyl bromides in the presence of a nucleophile? We end up getting E2 eliminations, right? Secondary alkyl halides, if we really have to, we'll go ahead realizing that we're going to get an awful lot of elimination and we're going to have to clean up our product, but we might get some. But if it's primary, especially if it's primary and it's benzylic or allylic, we can get pretty good yields of the SN2 reaction. So here's another example. Here we take a ketone, we react it with LDA to make the lithium enolate. We let this reaction go to completion. Then we add our alkylating agent to form our substituted ketone. In this case, this is the lithium enolate we form. Notice in this case, these are going to be considerably more acidic. As it turns out, these aren't very acidic. You might expect them to be, but they're not. And we get most of our chemistry from this lithium enolate. And in this case, our alkylating agent is this benzyl bromide. And we can see this is the new bond that's formed. Right there, that's the new bond. This is also useful with esters that have...
I was just wondering why that would be the new bond that would form if you had the formation of a primary carbocation with your alkylating agent, why that wouldn't rearrange.
This is done under basic conditions, so there are no carbocations, right? No carbocations are formed because it's strongly basic. And that's a good question. Remember, we never have carbocations under basic and strongly basic conditions. Yeah, we don't. Because under strongly basic conditions, most of our chemistry comes from anions and neutral compounds. And in fact, under strongly basic conditions, we purposely have the other cation, the partnering cation is an unreactive lithium cation. Where was I? Okay, so in this reaction, there's our ketone. We remove this proton. That gives us our lithium. We should be able to then figure out from that, and we can see there is the structure of our starting compound, and there is the alkylating agent. That's the new bond that's formed. It's also useful with esters that have protons on the alpha carbon. Esters only have one alpha carbon, and this one has some protons. We can react it then with LDA. Because it's non-nucleophilic, it's not going to attack there. If it did, you would just get a nucleophilic acyl substitution reaction. But because we use LDA, it can access that carbonyl carbon, and it pulls off the proton instead, and we get this anion. And then we can react that with an alkylating agent. There we see there's the ethyl group that we added. In this case, over here, we're adding a methyl group to here. There we go. So these actually go in high yields. I'm not quite sure why the enolates go in higher yields than the enolates of esters. Then I'll take a look for that. So enolates of beta dicarbonyl compounds, we've already discussed that they're considerably more acidic. The nice thing about that, of course, is that now we don't have to use things like lithium diisopropylamide. We can use alkoxides, which ethoxide, the conjugate acid, is ethanol, and its pKa is around 16. So it should be a strong enough base that it'll pull this proton off and make that reaction go to completion. We can just use alkoxides to make this. This goes mostly to completion. The reason that these are so much more acidic is that we can delocalize the charge to either one of the oxygens. So we have much more charge delocalization for the 1,3 or the beta dicarbonyl compounds. These enolates are very stable because of that charge delocalization. And the advantage is that we can use much milder bases to remove the protons in between. So as it turns out, what we're going to find out now, we're going to do this last reaction today. The ethyl acetoacetate ion we'll see is the synthetic equivalent of the acetone enolate. We'll see in a second. The reason is we can get rid of all of this junk after the reaction, and we'll see why. And it's the synthetic equivalent of this. Why would we use this instead of just using acetone and lithium diisopropylamide? Well, you saw that thing at the beginning. Lithium diisopropylamide is a very dangerous reagent to be using. It's expensive. We have to have special glassware and all sorts of special equipment to do the reaction. We have to do it under inert conditions. It's really just a pain in the neck. And they often give poor yields. Not always, but they often give poor yields. We can achieve the same or better results using acetoacetic esters. So let's take a look. And this reaction is called the acetoacetic acid synthesis. This is acetoacetic acid ester. Okay? So there's the acetic acid, and that's the aceto group that's bonded to it. That's why it's called acetoacetic acid. So we can take acetoacetic acid and we can easily remove one of these protons to make the enolate anion, and then we just add our alkylating reagent and we alkylate it, and the other product is just the sodium halide that was formed because this comes off as the Br-. This is still an SN2 reaction. Now, the way we do these, we typically do it in ethanol as solvent, and we often will just take ethanol, throw in some sodium metal, and make our sodium ethoxide in situ. Then we add our acetoacetic ester to get the anion. We let that sit for a while. We want this equilibrium to be fully established, and most of it lies over here. Then we add our alkylating agent. Why not just throw everything into the pot at once? So that's something to think about. Why not just throw everything? Why do we let it go? I'll give you a hint. Ethoxide can react with this compound. Remember the Williamson ether synthesis. Take a look for that. That's why we don't throw everything into the pot at once. So we can get that monoalkyl acetoacetic ester. Once we've made that compound, remember with esters we can react them with sodium hydroxide and heat and undergo a hydrolysis reaction. That we hydrolyze the ester to get the acetate salt, okay? That's the base-promoted hydrolysis of the ester group that we did in chapter 17. We can then quench that with an acid, and we get this, what we call a beta-keto acid. We talked about this reaction as well. They undergo a very facile decarboxylation reaction because you can form this six-membered transition state up here, 1, 2, 3, 4, 5, 6. We can easily push the arrows and spit off carbon dioxide and form this ketone as the product. And that's what we use the synthesis for. Notice now, in effect, there's the acetone and there's the alkylating agent. So that's why we talked about it as being the synthetic equivalent of the acetone enolate anion. So from 17, recall, these undergo very facile decarboxylation. We work it up, and the end result is the same as if we alkylated acetone here. This reaction is just much easier, and it actually goes in very high yields. So here's an example. We take our ethyl acetoacetate, we react it with sodium ethoxide and ethanol, and once we let that reaction establish, we add this alkylating agent, which is 1, 2, 3, 4 bromobutane. It's bromobutane. That bromobutane gets bonded to the carbon in between the two carbonyl groups. We undergo the hydrolysis reaction with aqueous sodium hydroxide. Then we quench it to get this carboxylic acid. We heat it up, and it liberates CO2 to form our now substituted acetone in 52 to 61% yield. So the yields aren't fantastic, but they're pretty good. We'll start here next class, but we don't necessarily have to stop after one alkylation. We can actually do more than one alkylation by just changing our conditions.